Good morning, everybody. Today we are starting with one of the topic of the syllabus, Ionic Equillibria. In this topic, we will be studying the different ionic substances which are in equilibrium. Basically, on the basis of these substances or their capacity to conduct the electricity, they are divided or classified into the two classes. The first class is called as the electrolytes and the second is called as the non-electrolytes. The electrolytes, these are the substances whose aqueous solution or if they are in a fused form can conduct the electricity. Those substances are called as the electrolytes, while the substances whose aqueous solution or their fused form cannot conduct the electricity, those are called as the non-electrolytes. So this classification is done on the basis of whether their aqueous solution or their fused form can conduct the electricity or not. Generally, we will be relating with the electrolytes in this topic. That means the substances which can conduct the electricity in their aqueous form or in the fused form. The electrolytes, they are again divided into the three classes. The first class, that is called as the strong electrolyte. The second class, weak electrolytes, and the last class, that is moderate electrolytes. Obviously, to conduct the electricity, the solution must contain the ions, then and then only the electricity can be conducted. Therefore, on the basis of the extent of ionization and the formation of the ions, these electrolytes are classified into these three classes. The strong electrolyte, these are the electrolyte which ionizes completely in their aqueous solution. Almost they ionizes completely. Those electrolytes are called as strong electrolyte. While the weak electrolyte, which ionizes to very small extent, those electrolytes are called as the weak electrolytes. And the electrolyte which ionize to about 50%, ionization takes place, those electrolytes are called as the moderate electrolyte. Let's see the example of this electrolyte. The strong electrolyte, for example, the salts like sodium chloride, potassium chloride, the acid like hydrochloric acid, these are the strong electrolyte. These are called strong electrolyte because in their aqueous solution they ionizes completely. That means here the number of the ions which are formed on ionization are very large. The example of weak electrolyte, the acetic acid, which ionizes very weakly to form the ions, and the moderate electrolytes. These are actually moderate electrolyte. The strong electrolyte may behave like the moderate electrolyte on the different conditions of temperature and concentration. For example, when the temperature is very low, therefore the strong electrolyte, they may ionize moderately, or even if the concentration of the electrolyte, strong electrolyte is very large, therefore they act as or they behave like the moderate electrolytes. So therefore here the temperature and at the different conditions of temperature and concentration, the strong electrolyte may behave like a moderate electrolyte. Now, as we have seen here, the ionization which is taking place for the weak electrolyte, they ionizes very weakly. Therefore, the extent of ionization is called as degree of ionization. The degree of ionization which is denoted by alpha. ionization is nothing but fraction of total number of the molecules that forms the ion is called as the degree of ionization of that electrolyte. This degree of ionization alpha, it is equal to the number of molecules ionized divided by the total number of molecules of electrolyte in the aqueous solution. So, the fraction of the total number of the molecules which undergo the dissociation or ionization, that fraction is called as the degree of ionization. Therefore, the alpha degree of ionization, the formula for it is the number of molecules ionized divided by the total number of the molecules. Now, the next term, that is called as the ionization constant. This ionization constant is generally denoted by K. Now, if we take an example of a weak acid, for example HK, this is a representative weak acid example which ionizes as H plus and A minus. This ionization is a reaction where equilibrium is established. Here, as this is a weak acid, therefore it ionizes very weakly and the concentration of H plus and A minus form is very low. Now here, if we apply the equilibrium law to this reaction, obviously as in this reaction the equilibrium is established. Therefore, at the equilibrium, the concentration ratio of the ionized form and unionized form remains constant. That is called as the equilibrium constant. So, by applying the law of equilibrium to this reaction, we can write K is equal to the concentration of the ionized form, that is concentration of the cation and anion their product divided by the unionized form. So this is the equilibrium constant, and we know that at the equilibrium the concentration of ionized form and unionized form remains the constant. This constant, equilibrium constant, this is also called as ionization constant. So, ionization constant is equal to the product of the ions concentration divided by the concentration of the unionized form. Specifically, this ionization constant is being defined as the product of concentration of ions divided by the concentration of unionized form. Now, we are going to take the relation between these ionization constants for the acid and the bases and the degree of dissociation. Let's take example, one of the example. A weak acid example we are going to take. So this is a weak acid, acetic acid, which ionizes as acetate ion plus H plus ion. Now here, if we consider that alpha is the degree of dissociation of this acid. If we consider that initial concentration of this acetic acid is C. Initially, when this acid is not ionized, therefore, their concentration of these two ions will be 0. Now, at equilibrium, what will happen? Some of the acid will get ionized. Alright? Now, alpha is the degree of dissociation of this acetic acid. Therefore, at equilibrium, the alpha fraction of these two ions will be formed. So at equilibrium, the concentration of these two ions will be, or the fraction of the ions will be alpha, while here the fraction of the unionized form remaining will be 1 minus alpha. Right? Now, therefore, these are only the fractions at the equilibrium. Now, concentration at equilibrium, if we multiply just by the concentration to these terms, so we will get concentrations of these ionized and unionized form at the equilibrium. So these are the concentrations of ionized and unionized form at the equilibrium. Now let's calculate the ionization constant for this weak acid. As this is ionization constant for acid, so we are having the prefix A, the ionization constant for acid. This is equal to, this is the ionization reaction. From this ionization reaction, we will first write the formula. The concentration of acetate ion into concentration of H plus divided by the concentration of unionized acetic acid. Now, these are the concentrations term we know. Therefore, we are substituting them here. The concentration of the acetate ion at equilibrium is C alpha into concentration of H plus, that is also C alpha, divided by concentration of an unionized form, that is C into 1 minus alpha. Therefore, this is C square alpha square divided by C into 1 minus alpha. So finally, the formula becomes Ka is equal to C alpha square divided by 1 minus alpha. So this is what is the formula to calculate the dissociation constant or ionization constant for the acid. Ka is equal to C alpha square divided by 1 minus alpha. Similarly, we can derive the formula for ionization constant of a weak base. Ionization constant of a base. Generally, if we take a representative example, this is a weak base which will ionize weakly as B plus OH minus. Therefore, the ionization constant for this weak base will be the concentration of cation into concentration of this anion divided by concentration of unionized base, weak base. Now, let's take example. One example. Ammonium hydroxide. This is a weak base which will ionize as NH4 plus OH minus. Now, therefore, similarly we are going to derive the formula like the acid. So, if we consider that alpha is the degree of ionization of this weak base, initial concentration, if we consider of the ammonium hydroxide is C. Initially, no ions are formed, hence their concentration will be 0. The fraction which is remain at equilibrium of the ionized and unionized form is, as alpha is degree of dissociation, so alpha fraction is a dissociated, and the fraction which is dissociated, same fraction will be formed of the NH4 plus and OH minus ion. That means alpha is the fraction of both ions formed at the equilibrium. Therefore, the fraction which is remaining unionized of this ammonium hydroxide will be 1 minus alpha. Now, the concentration at equilibrium. These are only the fractions which are present at the equilibrium. Now to get their concentrations, we have to just multiply these all terms with the initial concentration. So C into 1 minus alpha, this is the concentration of unionized form of a base at equilibrium, and this is the concentration of the ions at equilibrium. Now, the ionization constant for base, hence it is called as Kb. Now, we will first write the formula from the dissociation reaction. Concentration of the cation into concentration of the anion divided by concentration of unionized form. Therefore, we are going to substitute the concentrations at equilibrium C alpha into C alpha divided by C into 1 minus alpha. So this is C square alpha square divided by C into 1 minus alpha. So Kb is equal to C alpha square divided by 1 minus alpha. This is the formula to calculate the ionization constant for the base. If we know the initial concentration of the base, if we know the degree of dissociation of the base, we can calculate the ionization constant, which is nothing but the equilibrium constant for the base. Now, the next concept of Komal effect. Komal effect. This is the effect. I'll take one example, and with the help of example, we will see what is Komal effect. These two are the electrolytes. This is a weak electrolyte, while this is a strong electrolyte. Now, if this solution, aqueous solution of weak acetic acid is added with some of the aqueous solution of sodium acetate, therefore it is observed that the acetic acid, this dissociates as, this is the dissociation reaction for weak acid or weak electrolyte, and this is the dissociation reaction of sodium acetate. As this is a strong electrolyte, therefore this ionizes almost completely as the acetate ion and Na plus ion. When this solution, the aqueous solution of acetic acid, is added with small amount of this aqueous solution of sodium acetate, therefore it is observed that the equilibrium in this reaction, it shifts towards the left. Equilibrium shifts towards the left means this dissociation reaction rate decreases and the undissociation, this backward reaction rate increases, and more of this unionized form is formed. This acetic acid in the unionized form is more formed. That is called as the shifting of equilibrium. If we add this solution, aqueous solution of sodium acetate, into the aqueous solution of sodium acetate, the dissociation, that means the forward reaction, the rate of this forward reaction decreases and the rate of backward reaction increases to form more concentration of acetic acid. This is called as the Komal effect. Here condition here one is, these two electrolytes which are present, these must have one common ion in them. See here, this acetate ion is common here. Why this ionization is suppressed, that we will see. See, this is a equilibrium reaction, so it will have equilibrium constant which is equal to Concentration of acetate ion into concentration of H plus ion divided by the concentration of acetic acid. Now, we know that equilibrium constant remains constant once the equilibrium is established in the reaction. Therefore, once the equilibrium is formed, when we add sodium acetate aqueous solution in this solution, therefore what will happen? The concentration of these ions will increases to very large extent. Already ions are present in the solution acetate ion. When you add sodium acetate, very large concentration of acetate ion is formed, and therefore as this concentration increases, therefore this will be disturbed because this concentration has increased. This concentration, if it is increased, the value of the equilibrium constant will no longer remain constant, but the equilibrium constant, it has to be constant once the equilibrium is established. So for that purpose, what happens? Backward reaction rate increases. We say that the equilibrium is shifted towards the left side, to the reactant side, so that more concentration of the unionized form is formed. The reaction, backward reaction rate increases. These ions again come together and form unionized form, and its concentration increases. This concentration, if it is increased, therefore the increase due to acetate ion is compensated by the increase in the concentration of acetic acid, and this is again made constant. So therefore, to make this concentration large, the backward reaction has to be more. The backward reaction will increase its rate and more of this concentration will form, and therefore the concentration of these two ions decreases. So this is what is called as the common ion effect, which is simply defined as the dissociation of weak electrolyte is suppressed due to the addition of a strong electrolyte having a common ion with the weak electrolyte. This is called as the common ion effect. We can take many examples. For example, HCl and H2S. Here, H2S is a weak electrolyte which ionizes as twice of H plus H2 minus, while HCl which ionizes as H plus and Cl minus. This is a strong electrolyte, this is a weak electrolyte. If this weak electrolyte solution is added with this strong electrolyte, therefore the dissociation of this weak electrolyte is suppressed, that means lower concentration of these two ions is formed. So this is a common ion effect. The rest of the part we will see in the next lecture.